I want you to imagine, just for a second, that you are driving down a highway at like 100 miles an hour.
Okay, a little fast, but I'm with you.
Yeah, you have the steering wheel in your hands, your eyes are locked on the speedometer, and you feel like you are in total control. But then suddenly you pass out.
Oh, wow.
Right, the car is still rocketing forward, you are entirely unconscious. What happens next? I mean, in a normal car, you crash.
Yeah, you definitely crash.
But what if you had an invisible, entirely separate system buried in the chassis? Like a system that isn't connected to the steering wheel or the gas pedal at all? It doesn't help you navigate, but it detects that you've lost control and automatically slams on the brakes.
I mean, it's an incredibly comforting thought. You're essentially relying on a ghost in the machine, right? A silent guardian whose only job is to wake up and save your life when the primary driver fails.
Exactly. And while our daily commuter cars might not have that exact level of complete fail-safe independence yet, the world's most dangerous industrial plants absolutely must.
They really have to.
Welcome to this deep dive. Today, our mission is to explore a fascinating stack of highly technical engineering sources, including the Safety Instrumented Systems Engineering Handbook by Kenexis, a systems overview by Avanceon, and 2 incredibly detailed incident reports on the Piper Alpha and Deepwater Horizon disasters.
It's a heavy stack of reading.
It is. But we are going to decode exactly how the process industry engineers safety, taking apart the mechanisms that turn horrific tragedy into bulletproof protocols.
And we are looking at these sources because the infrastructure you rely on every single day, the fuel in your car, the chemicals that purify your drinking water, the pipelines heating your home, they all rely on these hidden, highly complex safety systems to prevent cities from being leveled.
Literally leveled.
Yeah, we are exploring how engineers calculate risk, quantify it mathematically, and physically build fail-safes to counter human error and mechanical failure.
Okay, let's unpack this, because before we can understand how these massive systems fail, we really need to understand how they're supposed to work on, a normal Tuesday. The sources talk about industrial automation having 2 distinct brains. What does that actually look like in a physical plant?
So, the first brain is the Basic Process Control System, or BPCS. You will also hear it referred to as SCADA, which stands for Supervisory Control and Data Acquisition.
SCADA. Okay.
Think of SCADA as the relentless optimizer. It manages the day-to-day, second-by-second operations. It opens valves, regulates temperatures, and keeps the pressure just right so the plant can actually manufacture the product it's designed to make.
So it's doing the actual work.
Exactly. Its entire purpose revolves around efficiency, yield, and real-time monitoring.
So if SCADA is the optimizer, it's essentially the driver, the steering wheel, and the dashboard of our highway car.
Yeah, that's a perfect analogy. What's fascinating here is that the basic process control system has a massive inherent vulnerability.
Which is?
Well, if sensor breaks, or a controller malfunctions, or even if a human operator just makes a bad decision based on a misread gauge, the BPCS can easily drive the entire process right over a cliff.
Because it doesn't know any better.
Right. It doesn't know it's making a mistake, it's just executing commands. That is why industry standards demand the second brain, the Safety Instrumented System, or SIS. The SIS is an independent protection layer.
The texts mention something called the SIS having 3 distinct parts: sensors, logic solvers, and final control elements. How does that actually physically look in a refinery?
Picture a massive pipeline carrying, volatile gas. The SIS has its own dedicated sensor on that pipe, completely separate from the SCADA sensor, quietly measuring the pressure.
Okay, so a totally separate set of eyes.
Exactly. That sensor feeds data to a dedicated logic solver, a standalone computer whose only job is to evaluate if that pressure has crossed a dangerous threshold.
And if it has.
If it has, the logic solver sends a signal to a final control element.
Right.
That might be a massive spring-loaded shutoff valve that slams closed to isolate the gas.
Wow. So it really is the autonomous emergency braking. It doesn't help you drive. It has nothing to do with getting you to your destination faster or making the plant more profitable.
No, not at all.
It only wakes up to save your life when a crash is absolutely imminent.
And the most crucial rule of this architecture, something the Kenexis Handbook emphasizes heavily, is absolute physical and functional separation.
Right.
The SIS cannot share sensors with the BPCS. They cannot share the same computer processors, and they cannot share the same valves. Blending the 2 systems is a catastrophic engineering sin.
Because if they share a component, a single failure takes down both the driver and the emergency brakes at the exact same time.
Precisely. Now, the basic process control system is allowed to ask the safety system for a favor, like, sending a digital request to close a valve for routine maintenance. But the safety system makes its own independent decisions based solely on its own separate sensors.
Oh, that makes sense.
Yeah, if the primary automation gets a virus or shorts out or loses power, the safety automation must not share that exact same flaw. It is a philosophy of total isolation.
Which makes perfect sense when you draw it out on a whiteboard. But as we see in the incident reports, even if you have perfectly distinct, mathematically isolated systems, they are still fundamentally operated by humans. And humans, well, we are messy. We assume things, we communicate poorly, which takes us to the human element of failure.
Yeah, and there is no starker example than the Piper Alpha platform in the North Sea off the coast of Scotland, July 6, 1988.
It's a tough one to read about.
It really is. This is widely considered the watershed moment that divided the history of industrial safety into a before and an after.
Yeah, according to the SHEQ network case study, Piper Alpha was a massive offshore oil production site, like a towering city of steel in the middle of the ocean.
Huge.
On this particular day, a vital condensate pump A, was taken offline for routine maintenance. The pressure safety valve was physically removed for servicing, and to plug the hole where that valve used to be, they installed a temporary blind flange. What exactly is a blind flange in this context?
A blind flange is essentially just a flat metal plate. It gets bolted over an open pipe to prevent fluid from spilling out during maintenance.
It's just a temporary cap.
Right, but crucially, a temporary blind flange is not rated to withstand the immense operational pressure of the active pump. It is merely a physical placeholder.
So the day shift maintenance crew finishes their work, but pump A isn't ready to be turned back on because it only has this temporary plate holding back the ocean of pressure? They document this on a paperwork permit?
Yeah, they filed the paperwork in the control room. But during the shift handover, when the day crew was briefing the incoming night crew, they failed to verbally communicate this critical detail.
Oh, wow.
The piece of paper was just sitting in a tray, but the conversation never happened. The night crew assumed pump A was ready for service.
So later that evening at 10 p.m., the secondary pump B, unexpectedly trips and goes offline. The night crew needs to maintain production targets. They see pump A is off, they don't see any active warnings on their immediate dashboard, and assuming it's fully operational, they flip the switch to turn it on.
And the condensate gas surged into pump A. The temporary blind flange wasn't secured to handle that kind of pressure.
It couldn't hold it.
No, it gave way almost immediately. High-pressure gas leaked out, quickly found an ignition source, and the resulting series of explosions and fires completely destroyed the platform. 167 lives were lost in a matter of hours.
Wait, I have to push back here. I'm trying to wrap my head around this. An entire offshore oil platform, billions of dollars of engineering was reduced to ash, and 167 people died because of what is essentially a missed sticky note and a bad game of telephone at 10 p.m.
I know.
It seems way too simple.
If we connect this to the bigger picture, it wasn't just a simple mistake by one or two guys who forgot to mention a valve. Lord Cullen led the official public inquiry, and the resulting Cullen report identified this as a profound systemic weakness in the culture of offshore drilling.
A systemic weakness.
Yeah, it was a complete failure of the permit-to-work system.
Meaning, it shouldn't have been possible for human memory to be the final barrier preventing a rig from exploding.
Exactly. The safety culture at the time was heavily reliant on decentralized paper trails. There was no unified, rigorous view of active permits.
Just trays of paper.
Right. A piece of paper in control room tray is useless if the system allows an operator to physically start a pump without verifying that paper exists. The Cullen report made over 100 recommendations that completely reshaped offshore safety, forcing the industry to abandon localized paper-based systems in favor of formal, verifiable safety management systems.
So how do you fix a culture? I mean, you eventually move to the digital permit-to-work software we see today, where you literally cannot flip the digital switch to turn on a piece of equipment unless the system verifies that all maintenance permits are officially closed out, signed off, and the physical lockouts are removed.
Piper Alpha taught the industry that human communication is a massive vulnerability. You have to engineer the overarching system to catch the human error before it translates into a physical catastrophe.
But, you know, if we digitized all these permits and made human communication foolproof, why do offshore rigs still explode?
Well, taking the human out of the loop creates a new, much more terrifying problem. What happens when a machine has to make a life or death decision entirely on its own and the machine starts to break?
Oh, man. Which brings us to April 20, 2010. The Macondo well blowout on the Deepwater Horizon rig.
Yes.
The Industrial Monitor Direct Engineering Report breaks down this failure, and it is a masterclass in overlapping mechanical doom.
This is a case where the sheer scale of the engineering is almost hard to wrap your head around. The primary barrier, the cement pumped into the bottom of the well, failed to seal it. Hydrocarbons rushed up the drill pipe toward the surface.
But there was a backup, right?
There was supposed to be a mechanical safety net sitting on the ocean floor, the subsea blowout preventer, or BOP.
The texts describe the BOP as an absolute behemoth. We're talking about an 800-ton stack of steel and valves operating at up to 5,000 pounds per square inch of pressure in the freezing dark of the ocean floor.
It's massive.
Its ultimate job, its final failsafe, is something called the blind shear ram. If everything goes wrong, this mechanism is designed to physically crush and cut through the massive steel drill pipe, sealing the well shut permanently.
And to cut through thick steel pipe, it needs immense hydraulic power. But in a catastrophic blowout, the BOP might lose its power and communication tether from the surface rig.
So it has to work on its own.
Right, so it relies on subsea accumulators to provide that crushing force autonomously.
The source actually gives the specific accumulator sizing rule formula used by engineers. It says the volume of the accumulator V sub AC is approximately equal to 7.5 gallons multiplied by a safety factor. But what does that actually mean physically? How does an accumulator work?
Think of an accumulator as a tightly coiled spring, but made of compressed gas. It's a heavy steel bottle filled with nitrogen gas that has been compressed to an incredibly high pressure. Beneath that gas is hydraulic fluid.
Okay.
If the rig loses power, a valve opens. The compressed nitrogen violently expands, and it pushes the hydraulic fluid into the pistons of the shear ram.
Oh, I see.
That 7.5-gallon formula is calculating the exact volume of hydraulic fluid required to guarantee the shear ram has enough kinetic energy to completely slice through the steel pipe. If you miscalculate that volume, the wedge stops halfway through the pipe, and the well remains open.
And on Deepwater Horizon, that automated BOP system failed to shear the pipe and seal the well.
Unfortunately, yes.
But the engineering report highlights something else that is just as terrifying as the mechanical failure. It's the psychological element of what was happening up on the rig floor in the minutes before the explosion. They call it the alarm storm.
The reconstruction of the driller's panel timeline shows a cascade of warnings that went completely unaddressed by the operators.
Let's walk through this timeline because it really paints a picture of what cognitive overload looks like. At T-0, the pit volume drops.
Right.
30 seconds later, at T plus 30 seconds, an alarm blares pit gain high.
Meaning the well is actively taking on massive amounts of volatile fluid.
15 seconds later, T plus 45, another alarm triggers standpipe pressure low. At 2 plus 60, whole volume overflow.
It just keeps coming.
At T plus 90 seconds, a massive spike triggers the gas high alarm. At T plus 120 seconds, flow line temp high. And finally, at T plus 150 seconds, the physical derrick itself starts straining under the immense pressure, triggering a hook load / drag alarm.
2.5 minutes of escalating, screaming alarms.
Yeah.
And the most haunting part, every single one of those alarms was completely valid. The sensors were working perfectly.
So if I'm the operator and I'm seeing a new critical alarm pop up every 15 seconds for 2.5 minutes, why didn't I just hit the big red emergency disconnect button to activate the BOP? Were they just frozen?
They were paralyzed by cognitive overload. This brings us to a crucial modern engineering concept called alarm rationalization, specifically outlined in the ISA 18.2 standards.
Alarm rationalization?
Yeah, the system was feeding them perfectly valid data, but it wasn't rationalized. In industrial automation, an alarm shouldn't just be a loud noise indicating a change in state. It needs to dictate a specific, actionable response from the operator.
It sounds like driving in heavy highway traffic, and suddenly your check engine light, your low tire pressure warning, your ABS failure light, and your oil pressure light all start flashing at the exact same time while a truck is honking at you.
Exactly.
You don't know what to fix first, so you do nothing.
That is exactly the psychological state. If you throw a dozen high-priority alarms at a human being in 90 seconds, they cannot process which alarm is the root cause and which is just a downstream symptom. It ceases to be information and just becomes noise.
Just pure noise.
Post-Macondo, regulators realized they had to step in. The standard now dictates that an operator should not receive more than 150 alarms in a single day.
Wow, per day.
Per day. In an emergency, the automation has to filter the noise, suppress the symptomatic alarms, and highlight only the critical life safety actions.
The report also notes that mechanical regulations changed heavily after this blowout. The API 16D standard now requires subsea systems to have dual independent MUX pods. What does that do?
So the MUX pod is the electronic brain sitting on the BOP that receives signals from the surface. They realized that a single failure, like a crushed communication cable or a blown fuse, could take down the entire BOP.
Right.
Now, you have a blue pod and a yellow pod. They are completely redundant and physically separated. This prevents a common mode failure.
Meaning a single event, like a fire burning through a specific cable tray or a piece of debris falling, cannot take out both the primary system and the backup at the exact same time?
Yes. The system is designed so that no single point of failure can prevent that blind shear ram from activating.
So we have Piper Alpha showing us how paper systems and human communication fail. And we have Macondo showing us how mechanical failsafes and alarm management fail. How do modern engineers actually try to prevent these overlapping disasters today? I mean, they can't just guess and hope for the best.
No, they don't guess. They use a highly rigorous mathematical approach called the safety lifecycle. This is codified in the IEC 61511 standard, and it is a true cradle-to-grave philosophy for building safety systems. It dictates how a system is conceived, built, tested, operated, and eventually decommissioned.
The Kenexis Handbook breaks this down. It throws a lot of acronyms at us, so let's translate them for the listener. It starts at the very beginning with the PHA, the Process Hazards Analysis.
Think of the PHA as structured, obsessive brainstorming. A team of engineers and operators sit in the room for weeks. They systematically look at every single node, every pipe, and every vessel in a plant design, asking, what happens if this fluid gets too hot? What happens if the pressure spikes here? What happens if this valve gets stuck open?
They are hunting for the hazards.
Exactly.
And once they identify a hazard, they design a SIF, a safety instrumented function. This is a very specific action taken to stop a very specific hazard. The book gives a great example. Boiler flameout due to low pressure causes shutdown.
Right.
It's essentially an if-then statement coded into the system. If the flame goes out, then slam the fuel valve shut.
But not all hazards are created equal. A small cooling water leak is annoying. A high-pressure toxic gas leak into a populated area is lethal. That's where the third acronym comes in, SIL, or Safety Integrity Level.
Here's where it gets really interesting, because you don't just buy a generic safety system off a shelf. SIL is ranked from 1 to 4. I like to compare this to buying a lock for a bicycle.
Okay, I like that.
If you live in a super quiet, safe neighborhood, you might just buy a cheap $10 cable lock. That's your SIL-1. It offers some basic protection. But if you are locking up a $1 million gold bar in the middle of Times Square, you don't use a cable lock. You build a titanium vault with a retina scanner.
That's a good way to look at it.
That's SIL-4. You don't put a SIL-4 system on a minor water valve because it's wildly expensive, incredibly complex, and requires constant testing. You fit the armor to the threat.
And the standard is strictly performance-based, not prescriptive. It doesn't tell a plant owner what brand of valve to buy. It tells them how mathematically reliable that valve must be over time. SI-1 gives you one order of magnitude of risk reduction, meaning 90 to 99% safety availability. It will work 9 times out of 10 when called upon.
But SI-4.
SIL-4 provides a risk reduction factor of 10,000 to 100,000.
Wow.
That is over 99.99% availability. And to achieve that level of mathematical certainty, you have to build in what we call hardware fault tolerance. You calculate the risk, and you build the exact amount of physical redundancy required. For example, implementing a 2 out of 2 voting system.
Meaning you have 2 separate sensors monitoring the same pipe, and both must agree there is a dangerous pressure spike before the system shuts down the plant.
Or 2 out of 3 voting system, where you have 3 distinct sensors, and if any 2 agree, the system trips.
Oh, clever.
Yeah, this architecture prevents a single faulty sensor from causing a multi-million-dollar false shutdown, but it guarantees that if a real emergency happens, the system will absolutely catch it. And these components undergo constant diagnostic coverage tests.
Wait, diagnostic coverage test. Break that down for me.
It's essentially the safety system constantly checking its own pulse. It might send a microscopic electronic signal to a massive shutoff valve just to see if the valve stem moves a fraction of an inch.
Just a little nudge.
Right. It doesn't move enough to disrupt the flow of oil, but it moves just enough to mathematically prove to the logic solver that the valve isn't rusted shut. Post-Macondo, those subsea BOP deadman switches we talked about, they are now legally required to meet SLL3 standards, demanding this exact kind of continuous self-diagnosis.
That requires a massive amount of engineering, testing, and math. And, it all brings us back to you, the listener, because we don't often think about this as we go about our day.
We really don't.
We walk past industrial facilities on our way to work. We ride on trains carrying hazardous chemicals. We drive past sprawling refineries and rely on underground pipelines every single day.
We live our modern lives surrounded by immense amounts of trapped energy.
We do. And we are protected by these invisible safety life cycles. We're protected by engineers sitting in rooms obsessively debating SI levels, calculating subsea accumulator pressures, and running diagnostic coverage tests, all so that we don't have to worry about the sky catching fire while we commute.
This raises an important question, though. There is a caveat to all of this, and it's a chilling one tucked away in the final pages of the Kenexis Handbook. It's a regulatory concept called grandfathering.
So what does this all mean for existing plants?
Well, IEC 61511 and modern regulations are incredibly strict when you're designing a brand new facility today. But they often allow existing equipment plants that were designed and built to older, less rigorous codes decades ago to remain in operation.
Wait, really?
Yeah. Provided they are deemed to be maintained and operated safely, a company doesn't necessarily have to rip out a 1980s control system just because the 2026 standard was published.
Wow. Which leaves us with this final thought. The next time you are driving down the highway at 70 miles an hour and you pass a 40-year-old refinery or chemical plant looming on the horizon, ask yourself, is that facility running on the modern SIL3 dual-pod rationalized alarm standards we just talked about? Or is it grandfathered into the safety standards of the 1980s?